So the stream of people is slowly going to zero. So let's start the next session. I'm happy to moderate this session with Richard Stearns and Madhu Sudan. My name is Reinhard Wilhelm. I'm the delegate of the Leibniz Center for Informatics in Schloss Bergstuhl. In my previous life, I was having a career as a compiler person, and one particular area of work was attribute grammars, for whose invention Don Knuth did not receive the Turing Award. Attribute grammars are long given up. They used to be also it was expected that they would serve as description mechanisms for the static semantics of programming languages. And so when I started working there, I was seeing references to Richard Stearns, and I was convinced that his first name was Louis, his second name was Rosenkrantz, because there was a famous paper by Louis, Rosenkrantz, and Stearns on attributed translations, which you had to read when you were working in the area. So, but Richard is not Louis nor Rosenkrantz, only Stearns. And he later turned to complexity theory, and with Juris Hartmanis laid the foundations for complexity theory and received the Turing Award for this. Okay, so today he will speak about something that nobody of us knows, canalizing functions, whatever that is. Please.
Thank you. Well, I'm going to talk about canalizing functions, not because they're important, because they're fun to play around with. So if you don't know what they are, that just goes to support my contention that they're not important. Also, I'm going to, during the talk, I'm going to emphasize the process whereby we perform our research and see what these functions are doing and try to draw our conclusions. And without trying to throw all the algebra at you, which finally supports those conclusions. Okay, now this work was done jointly with Dan Rosenkrantz and Ravi, who are, the three of us are retired faculty from the University of Albany. And by Madhav Marathi, he was a student of ours many years ago. He's since risen to be a important part of the Virginia Tech. He brings in a lot of grant money in respect to homeland security and threats. So the first curious fact is why this is at all interesting to homeland security and threats. Okay, so these are the research methods I'll be discussing. First thing is to get a mathematical understanding whereby we can solve a sum n plus one parameter problem by first solving an n parameter problem. And you'll see by the iterative nature of the definition why this is likely to be successful. And after we understand those mathematics, we can program our solutions. And then it's easy to work out examples and experimentally look for patterns. And once we have a conjecture, then we can prove them with the algebra suggested by the programs. So these functions are all binary valued functions, or 0, 1 as we're going to use during this talk. Well, finally, to the definition. First, we'll define canalizing and then nested canalizing. So a function is called canalizing if for one of its parameters that can be expressed as indicated on the slide, the first statement, if the value of that parameter is equal to A, then the value of the function is B. And otherwise, the value of the function is some function of the remaining parameters. And the function is called nested canalizing if when we say function of the remaining parameters, that is also a canalizing function, and so forth. So a canalizing function then might be described thus, which says, well, if the value of parameter v1 is equal to 0, then the value of the function is 1. Otherwise, we perform a second test, and that parameter has value 1, then value of the function is 0, and so forth, all the way down to the end. And then finally, if you fail the final test, there's some default value, in this example 1. Okay, well, we don't like the idea of the last statement being that the default value is the same as the output value for the last variable, because in that case, the function does not depend on the last variable at all. And we're just excluding them from the talk. Not that one couldn't add them on, but we choose not to. And the bottom line then is therefore the final then and the else parts must be different. Okay, so this enables a simpler notation shown on the right here, where we list the name of the parameter and the test condition and the resulting output if that condition should hold true. So first rule then says, well, if v1 is value 0, then we'll output 1, etc. Now, because of the last slide, we've ruled out the default being the same as the output of the last rule. We don't even have to say what the default is, because you see the rule for parameter 9 is 1 goes into 0, and therefore default value would be 1. Okay, well, we have here two descriptions which are equivalent, and notice these two descriptions are entirely the same, except for the last variable. And of course, if you say, well, if that parameter has value 0, the output is 0, and saying, well, if it's 1, the output's 1, those are two ways of saying the same thing. So we come to agreement that we'll always make the output of the last rule match the preceding rule. So in this case, it's the one on the left that we're using and not the one on the right. Okay, now these functions do actually have an application to biology. So even though they're fun to work with, this concept was originally proposed by some biologists. The second curious fact is that originally they were spelling it with an I instead of a Y. And then later on they started spelling it with a Y. So that's not a misprint, that's the way it is. Okay, now this next slide shows the concept of a layer. Notice that I've grouped the rules into 3 groups here. In the green group, they all have output 1, and then in the red group, output 0, and then finally, the last group with blue again is output 1. And so within a layer, you have the flexibility of switching the rules around. So the second column is the same as the first column. That is, it doesn't matter in which order we test the variables, two parameters 2, 3, and 1. If any one of them tests succeed, the output is 1. Whereas if we were to change the, go to other arrangements, that would change the value of the function. Okay, now this shows that there is a certain simplicity when the layers have several rules in them, which suggests that if we were looking for extreme examples in some cases, for some problem, that we'd want as many layers as we could have. So if we're looking for counterexamples for something, the obvious place to look is where you have as many layers as you have variables -1 because we've agreed that the last two rules belong to the same layer. Okay, so we're going to examine curious facts in two areas. One is in the area of representing a nested catalyzing function with a threshold gate. And then the curious thing is that we see the Fibonacci numbers showing up as threshold weights. And the second is an analysis of worst case average sensitivity, in which case we'll see that suddenly the odd number parameters and the even number parameters are treated differently. All right, well, what is the threshold function? Well, it was explained this morning. Each parameter has a weight. Weights may be negative. And there's a threshold value. And if the sum of the weights for the parameters which have input 1 is greater than the threshold, then the value of the function is 1. Otherwise, it's 0. Okay, and these are the things we want to show. We'd like to show that any NCF is also a threshold function. Second, that you can find these weights in polynomial time. And then thirdly, that the worst case, the largest integer weight, is exponential in the number of variables, which you'd expect if those weights are going to be Fibonacci numbers. Okay, so here's how we're going to compute the weights inductively from a description. And we're going to start with the last parameter first. And we want to compute a weight for each parameter based on the weights already picked. And in order to program this, we're going to have to keep 3 variables: a threshold, the sum of the positive weights, and a sum of the negative weights. Okay, and then for each type of rule, we're going to have a way of getting from the smaller number of parameters to the larger number. So, as it says here, each rule we're going to have, each type of rule we're going to have a plan. So I'm going to describe the inductive rule for rules of the form 1 goes into 1. And I'm not going to present the other ones. If after the talk is over you beg me, maybe I'll explain what the others are. Okay, well first the mathematical facts. The weight for the parameter vi has to satisfy this condition. Well, why is that? Well, the rule says that when the value of the parameter is 1, the value of the function has to be 1. And that means that regardless of the other parameters, you have to exceed the threshold. Well, what is the worst case? Well, the worst case is that with the parameters with positive weights all have input 0, and those with the negative weights have input 1, in which case the sum of the weights then is Wi plus all those negative weights, and that has to be greater than the threshold. So this is simply a mathematical fact. And of course, what is the minimum integer weight that will do that? And that's, of course, t minus the sum of the negative weights. So this is the mathematics, and now we program that. Take the following actions. We set the weight to be the minimum weight, which we know mathematically it's supposed to be. And of course, we've created a new positive weight, so we have to add that to the sum of the positive weights. Okay, so here's what we think of ought to be the worst case, namely where the outputs alternate so that each rule is in its own layer. And so we run through the calculations, and we find these are the weights. And you can see these are the Fibonacci numbers. So we've discovered these and be interested in proving why. Okay, well, let's make, this explains why this ought to be so. This isn't exactly, this is not a proof, but an indication. Namely, if you set the variable vi equal to 1 and the next two variables 0, you have to get the same result as if the variable was set to 0 and the next two are set to 1, because the rules alternated in output. And in order for those to have the same effect, you want the weight of for parameter I to be equal to the weights of the other two. So one expects the Fibonacci numbers to come in. Okay, well, let's make change the problem slightly, where, for example, for the rule for V3, instead of having 1 goes into 1, let's have 0 goes into 1. And we've changed several of them. And this is the result. And you see that, yeah, the Fibonacci's are there again. It's just that you see that it's the absolute values which fall into the Fibonacci series. And so the actual rule is about the absolute values. And the threshold is changed. Now, why are some of these negative and some of these are positive? Well, the rules 1 goes into 1 and 0 goes into 0 both make the function increasing as a function of the corresponding variables. And where you have 1 goes into 0 and 0 goes into 1, the function is decreasing as the function of those variables. And so where they decrease, the weights are negative, and where they increase, the weights are positive. And just briefly, I'm not going to explain all this, but what happens if it's not the worst case? What happens if there are just a few layers? And you can see that the weights in each layer are the same absolute value. And no surprise there, since we said you could perform those tests in any order, and there is a formula that explains that, which we will not go into. And of course, to prove then that the Fibonacci numbers are the worst case, then you need to bring in some algebra to support that claim, which I'm not going to do. So let's see. This is a check. This is a countdown clock. Okay. Okay, well, let's talk about the other topic, namely sensitivity, which will explain what sensitivity is with an example. So we're supposing that the value of the function shown in blue there and inside the rectangle is as shown as output 1 for those assignments to the inputs. And then we look at the effect of changing any one of the values. And so in this example, if you change the first bit, that doesn't change the output of the function. If you change the second bit, it does, and so forth. And we observe that 4 of the 7 cases, changing one input bit changes the function. And therefore, the sensitivity of this input assignment is 4 by definition. Okay, well, we're interested in the average sensitivity, which you get simply by adding all the sensitivities and dividing by the number of possible input assignments. Okay, so the question then arises, and asked by these biologists, what is the worst case average sensitivity for an NCF as a function of the number of variables? Well, we already know that we should conjecture that the worst case is where the outputs alternate. And a second thing, which we're going to be able to answer, is to describe the set of all the functions which have the worst case. So this is the candidate then for the worst case, and it's with the alternating outputs, except of course the last 2 variables, which we require to be the same. And in this case, when we do the calculation by means we'll be discussing, we see that the average sensitivity is 1.33203, and that's very close to 4/3. So it was conjectured by these 5 authors that the average sensitivity was never larger than 4/3, and that the alternating example is the worst case. And then the second 3 gentlemen explained, using Fourier analysis, that they found an exact formula for the alternating example and were able to show it was the worst case. So that's another curious fact, that using Fourier analysis instead of simple algebra, they're able to get the answer. All right, well, so here is the worst case example, and as explained, this is the average sensitivity. But we're going to make a change here, and notice that in the 2 green variables, the outputs alternate, and for the red they alternate, and the blue and so forth. But between boundaries, they do not alternate. That is, between going from the rule for input V2 and the output for rule V3, they have the same output. So there are, the alternating case is certainly is not the only worst example. Well, suppose we do the alternation slightly different. Here we've grouped 2 and 3 and 4 and 5 together. And now the average sensitivity is less. So this is the curious fact that the even-numbered parameters are treated differently than the odd-numbered parameters. Okay, well, let's get into how we actually compute these. First, we need a little terminology. So I'm going to use A subscripted I to be the condition for input I, and the B with subscript I to be the output. And then I'm going to write tilde 1 to mean 0 and tilde 0 to mean 1. So in order to build up rules for actually computing the sensitivity, there are several things that suggest that we need to know. So we're going to talk about the set AI, which is a set of input assignments where the earlier variables have been set so their conditions fail. And of course we know the size of the set AI, namely it's just 2 to the number of the remaining parameters. Then we're going to have an AI with subscript 0 or 1, and that's going to be the subset of AI where the value of the function is either 0 or 1. And of course this will partition the set AI, so the fact shown in blue is that AI is the union of those two sets. Okay, and the third set we want to pay attention to is that the set of is a set of input assignments where changing the value of the parameter I changes the value of the function. Because that's so, and of course the average sensitivity is going to be the sum of those of the SIs. In other words, we're just counting the number of ways that changing variable I will change the value, and that's going to be the total sensitivity, which we divide by the total number of assignments. Okay, and where there's certain relationships we can establish between these things, and I'm going to interpret the black things in black, and if you don't believe, maybe you can read the green, but I'm not recommending that you do that. So the first line says, well, if you want to know how many things, how many vectors where you're in AI, where the output is the output of the rule, well, that happens in two ways. One of the way is that the bit itself has been, meets the condition. And that's where you get the 2 to the n minus I. And the other is where it doesn't meet the condition, and then the value depends on the remaining variables. And because that's the number, that's the things in A of I plus 1, where the output matches the output of the rule. And the second thing says that, well, if you want to know how many things have a different output than the output of the rule, that's just a set of things that where the remaining parameters give you that output. Okay, and then the final thing says that if you want to know how many input vectors there are, in which changing the value of the ith bit changes the value of the function, why it's any vector where the value is determined by the remaining bits, since then you're changing the bit makes the condition satisfied, and by changing the value. And of course the opposite is true. You change the bit back and it switches back. So that's where the 2 comes from. Now these are enough to compute give you the average sensitivity for the for any example. As you take the results of the smaller thing and you use these formulas to find you can compute all the things on the left from the things on the right. So that's where the numbers we showed the earlier slides came from. Well, how does this going to help us with a worst case example? Well, you can try to find a closed form for the worst case example simply by plugging these things in. Well, when we tried that, a very peculiar thing happened, a curious thing happened, which we'll describe next. So, I'm going to ask the question for 2 consecutive input bits. What is the sum of the cases where changing the ith bit changes the value of the function, and plus the number of where changing the ith plus 1 bit changes it. And using the formulas from the previous slide, we see that it's 2 times this sum. Okay, well, we did, on the previous slide, we did have a rule for this. So let's plug in the, let's replace that with the rule we had from the previous slide. And we get this. Well, next thing we notice that if we look at these 2 terms, and if I assume that we're alternating, that is, if in which case BI would be different than BI plus 1, then with that assumption, this is just a partition of A to the I plus 2, and combining the 2 parts of the condition, we simply have A of I plus 2. So with that assumption, we replace this, and then, of course, we know how large that is, and that's this amount, and we add them together and we get this. Okay, well, what have we discovered? Well, this is what we've discovered. We've discovered that adding these 2 things together and making this assumption that the total number of things in these 2 sets is a function which is independent of any of the rules. So, this is then going to be a big help in getting a closed form as to how many of the average sensitivity and these worst cases. So this is where suddenly the alternations become a big help. Okay, so let's look at an example now where the number of rules is even. And we look at the first 2 rules, the green ones, and according to the lemma from the previous slide, the number of cases where changing those bits changes the value of the function is 2 to the 10th. And for the red ones, it says it's 2 to the 8th, and so forth, down to the black, which our lemma doesn't tell us what that is, but by inspection we see that that's 2 to the 2. So we simply add these numbers up using high school algebra, and we get the calculation shown in black here, and when I put in the number n instead of the number 10, we get the thing that's shown in blue on the bottom. On the other hand, we want to look what happens when n is odd. And so starting from the top, our lemma now tells us that there are 2 to the 11th cases where the changing that bit changes the value of the function, and 2 to the 9th and so forth, down to the very bottom where by observation it's 2 to the 1. So to get the average sensitivity in this case, again, we do our high school algebra, and what we get is shown in blue on the bottom when we put in an odd value of n. And so that shows then we have, now we haven't proved that this is the worst case sensitivity, and I'm not going to prove it's the worst case, so I'm just asserting that it takes work to make that proof. But we've shown that when the output of the even-numbered rules is opposite of the preceding rules, then these are the worst case sensitivities. So not only have we shown it for the alternating example, but we've covered all cases where the average, all cases were the worst case, and the worst case coming about because the even numbers are treated same as the odds. And you can stop here, and thank you for listening.
Yeah, thank you very much. We have time for a few questions. So I have a question.
Yes.
The results, how do they retranslate to biology?
What is the...
Is there any implication for biology?
Well, there some biologists think so.
Okay.
That's the... I think the idea is that either one gene determines what happens or the remaining genes do. Mm-hmm. I think it comes from that.
Okay, and also sensitivity and this all.
And yes.
Mm-hmm. Okay. Manuel?
Thank you for the talk. One question. What does Catalyzing come from?
Okay. Okay, well, Canalyzing with an I means to make canals. So to make canals, it's a legitimate word. So, for example, if you have a riverbed and you want to have ships go along, and you make it into you transform it so that it makes so ships can travel on it. And I think it also means to dig separate canals. But why a biologist would use that term, I have no idea.
Last question. No more question. Thanks again.